Architectures. This is a sequential architecture for deep learning models. And we can build many different types of models within a sequence of layers approach where you have a representation followed by universal approximation. But this is only one example of an architecture. An architecture is an arrangement of layers within which a model of a particular structure is learned. Sequential architecture, sequence of layers, we just saw that. In this video, we're going to look at some other architectures. A model occurs within an architecture. Popular references, autoencoders, GANs, transformers. Most often, they're not talking about models, they're talking about architectures. And you can have many different models within the same architecture. So deep learning neural networks, you've got convolutional neural networks where neural layers are combined with convolutions. Recurrent neural networks, later layers may feed back to earlier ones. Neural networks can have dynamics. Autoencoders, unsupervised artificial neural networks, Boltzmann machines go beyond Hopfield, and many more. And these are all architectures upon which we build complex mathematical models. Let's begin with autoencoders, which are going to be very important for us. An autoencoder is an encoder followed by a decoder. You have a bottleneck in between the two. This is a dimensionality reduction to latent space variable z. And your goal typically is to learn the identity transformation y equals x. Recurrent neural networks. Each cell has memory. Memories can feed back during the feed forward. Networks are dynamic. They have a sense of time. But note, not just for time series, other applications as well. Often used when the data is in the form of text and documents. Given a sequence of words, can predict what the next word will be based on learning next words from huge collections of relevant documents. Our example will be a long short-term memory, LSTM, from the PyTorch documentation. This is what an LSTM network looks like. It's good for text data where sequences of words are important. Generative adversarial networks. This is where you have two neural networks. A generator creates fake data, and a discriminator classifies real versus fake. So they're competing with each other. And the key is in the training. It uses duality via KL divergence. And specifically, it's a two-person game. The discriminator and the generator are trying to outdo each other. And then there is this newest architecture called a transformer. Inputs next to outputs at the same level. Positional encoding model structure. Multi-head attention is a model of query plus key gives you a value, much like what we do when we Google. Each of these is a neural network. Outputs can be either learned or generated. It's a generative model. And it needs huge amounts of data. So for ChatGPT, the T, for example, is for transformer. And notice that it's made up of these multi-head attention modules, each which is made up of scaled dot product attentions. And notice the transformers are based mostly on linear algebra. So if we look, we have matrix multiplication, dot products, linear layers, that's just matrix multiplication again. And there's another linear layer, again on the far right. Add normalization, those are linear processes. Inputs are word embeddings, which is words as vectors. And we have positional encoding, this uses Fourier vectors. We do vector addition. But we also have the neural network concept. In particular, we have a key concept, which you see in several places, called the softmax activation. So let's start with a model of a probability distribution on R objects where each of the probabilities is positive. So P sub y the Wythe probability can be written as 1 over z e to the negative phi sub I for some phi sub I in R, and z is our partition function. We can define an activation function motivated by this model as e to the negative z1 over capital Z, e to the negative z r minus 1 over capital Z and the negative z sub r over capital Z, that vector, which looks something like this when we put in the definition of the capital Z. And the image coefficient sum to 1, so we only need r minus 1, and so we can multiply the top and the bottom by e to the zr and get something like this. And that looks something like this with the assumption that we've subtracted each one of these from zr first. The reason I write it like this is because we only need r minus 1 of these image functions. They sum to 1. And if r equals 2, we get 2 of these functions. And you only need one of them. So if we use the last one, then we have logistic regression. That is, softmax is multi-class logistic regression. Now, we often talk about the softmax transformation, which looks like this. It has many different interpretations. So you can think of it as generalized linear separation. Logistic regression is a linear separator, and that generalizes to the idea if the classes are convex in feature space, then we can linearly separate. So if we have classes that look something like this, we can separate them linearly. We also have an unconstrained maximum entropy model, and we have a method for looking at relative feature importances. Most important, like logistic regression, softmax can be applied multiple times to transition from one model to the next. And you see that in our transformers. Now, that means we should think of our transformers as architectures, scaffolding perhaps, for many submodels. And you can kind of see where a submodel ends in some sense by noting where the softmax is. So, what is a transformer? Well, words go to vectors. That's feature engineering. Positional encoding models the sequence structure of words in a sentence. That's also feature engineering. Scaled product attention. We have a query matrix and a key matrix. And we take Q times K transpose. We rescale by D sub K, the column dimensions of Q and K. Mask, that's optional. And then we apply the softmax. And we get a matrix A. And matrix A is in R, Q cross L. And notice that all of its coefficients are between 0 and 1, so A is an affinity matrix. So we're supposing our sentences have at most L words. And that means we're going to get L vectors in RP. And we're going to construct that as a tensor in RL cross P. Positional encoding is also in RL cross P, and our V is going to be the sum of the X and the P. We're going to have scaled dot product attention again. A is in RQ cross L. That's Q queries on L words. Remember, there are L words in a sentence. AV, each query is a, quote, word in RP. It's an embedded word vector. And AV is a sequence, therefore, of Q words predicted from keys in K using input stream V. And now we can go on to the add and norm, but we're not going to do that here. See, this is all driven by the fact that sentences have structure, as do queries. So before we talk about all the individual parts, in the next module, we'll talk about why we use this kind of a structure. But preliminarily, notice that most data sets have structure. Word order matters in a sentence. There's a relationship between a given pixel in an image and those pixels around it. Data is often from a complex process with an underlying topology. Architectures allow deep models to learn structure by implicitly defining a model within the architecture. That brings us to the concept of transfer learning. A pre-trained model is a model trained on big data for use in models with the same architecture. Why? Well, you have a relatively small data set not represented in the data used to train the pre-trained model. Then you can apply the pre-trained model by using the pre-trained model's parameters as initial values in your new model and then train as usual. Or freeze the pre-trained model, no more training of the pre-trained model, add layers around it, and then train the new layers. So let's look at the example ants versus bees. We have 120 training and 75 validation images for each category. That's not very many. But we're going to use ResNet 18, greater than 1.2 million images over 1,000 categories. So we have our ResNet 18, but it was not trained on ants or bees. So our first approach, ResNet 18 as initial values of the parameters, and then we retrain the network. So here's what the code looks like. Notice we load our ResNet 18 model. Oh, the pre-train has 1,000 features, but we only have 2 features. So we're going to have a new model that has only 2 features. So we use this linear layer to transform from the 1,000 features to just 2. And then we're back to just the usual approach to neural networks. Now the other thing we could do is we could freeze ResNet 18 and add layers. In which case, we're only going to train the new part. Now we'll go forward on the entire thing, but we'll only train the new part. Here's the freezing code. Essentially, freezing means turning off derivative calculations. And then that leads to the concept of a foundation model. A very large AI model trained specifically to be frozen and then fine-tuned via transfer learning. Generative models in the next module. Pre-trained GPTs trained on the entire internet, for example. And transformers, an architecture with many submodel units, each playing a specific role, as we saw above. Nearly all open source foundation models can be found in huggingface.co, not com.co. Here's an example of somebody who's collected a bunch of foundation models. Hugging Face is a community-driven repository and collaboration site where you can find what others have posted and post for others to find. So foundation model redefines transfer learning in that the pre-trained model is constructed to be transferred. In particular, the foundation model itself is dictated by the big data used, and very often we choose incredibly large and very complicated sets of big data, not to train a final model, but only to train a foundation model. And then we do transfer learning. Fine-tuning, where the foundation model can be used, for instance, as a single layer, and we initialize it with the parameters, and then we tweak the parameters. And then prompting. This is where we've frozen the foundation model, and we add new layers that can understand our prompts. So architectures contain models. Big data is high variety. The structure of the data has important information. Individual models, however, are just functions. Inputs go to outputs. So we need the ability to model structure, not simply input to output. We may have very complex topologies, in which case we'll use complex architectures, often intentionally encompassing multiple scales. Not the models themselves across multiple scales, but the architectures addressing multiple scales. Often all but the final training is often already done for us. It's one of the advantages of architectures.